Great.
So take it away, Dennis. It's all yours.
Morning. Can you confirm that you can see my PowerPoint presentation?
Yes, we can. Oh,
Okay,
wonderful
wonderful.
images, all kinds of things, including the Auburn football symbol or something. Okay.
Let me jump into it right away. So I will talk about charge exchange. I know that there are a lot of people from different backgrounds here. So charge exchange is a process where a highly charged ion, typically with no electrons or maybe one or two, captures an electron from an unsuspecting neutral molecule. In our case, that's going to be molecules. In the graphic here, I show you an ion incoming in the red, capturing an electron from a hydrogen atom, going from left to right. The ion flies through the electronic cloud. The two particles are in a quasi-molecular state for a while, and then the electron has to decide with whether it stays with its initial atom or is captured by the ion here. It's captured into a highly excited state and goes to the ground state emitting an X-ray. So in the solar wind, you will have typically ions that are of atoms that are abundant in the sun. So hydrogen and helium foremost, but then also carbon, nitrogen, and oxygen, and a bunch of heavier stuff. These ions have typical freezing temperatures of about 1 to 2 million kelvins. Once they leave the solar corona, they are a collisionless plasma, so the temperature doesn't really have a meaning anymore. They move around the solar system with velocities of 250 to 1,000 kilometers per second, so that's up to about 1 kilo electron volt per AMU, and it's a very variable plasma. Okay, next slide. So there's a lot of charge exchange in the solar system. I've showed 3 examples here. On the left, you see a beautiful image of Jupiter, an optical image overlay with its aurora on top. In the middle, you see a very blurry picture. That's an XMM image of Mars, where the 2 different colors indicate different processes. You see that circle in the middle, which indicates the disk of Mars, a very dense atmosphere, where the X-ray emission comes from fluorescence, and in the blue and green around it, this is charge exchange emission from atoms that are escaping Mars, since that you know that Mars has not a lot of water on its surface anymore, and it has a very large exosphere of escaping gas. On the right, you have an image from Swift, where in blue you see a cloud of molecular gas, OH in this case, and in red you see X-rays, and the X-rays are offset towards the sun because the cometary atmosphere is collisionally thick. So you have charge exchange in front of the comet, but not behind it. I've given references to 3 review papers at the bottom here, Anil Bardwai, Konrad Daniel, and Brantwardi et al., which are great resources about X-ray in the solar system. Charge exchange emission is about to be used also to study the interaction of the Earth with the solar wind. There are 2 upcoming missions here. On the left, you have the European-Chinese mission called SMILE. I believe that's 2023. I forget the years. And on the right, there's a 6-unit small sat led by Boston University, which is called Cupid. All right, so from those slides, this is a little political thing I wanted to show. You see that this is a very interdisciplinary field. It includes heliophysics, planetary science, and astrophysics, which is great until you come asking for money, of course. So my specialty is comets. So let me explain in a couple of minutes why we like comets so much. So comets, different from planets, they move around the solar system often on elliptical orbits. So you get close to the sun, you get far away from the sun. They're also observable at different heliocentric latitudes. And that matters because from this complicated plot on the right, you see an X-ray image of the sun, and those wiggly lines are solar wind velocities. So you see that in the equatorial plane, you have low solar wind velocities, but at higher latitudes, you get a much faster wind. And also, these are not just moving at different speeds; these are also different plasmas with different temperatures. So you get to see a lot of different environments. The second thing is that comets are extended sources as opposed to point sources. And that means that you can do all sorts of investigations where you look for plasma structures. You can see how the solar wind moves through a cometary atmosphere, but you also can see the neutral distribution. And there's a blurry picture here. This is Comet Encke. And what you see towards the right is a fan of neutral gas that is blowing out of the nucleus. Now, the third thing that you can do is that comets are not steady state objects. They vary. Comets have outbursts, as you see in this picture in the top. This is an image taken from a spacecraft, the Rosetta mission, that captured an outburst of comet 67P while it was orbiting it. The sun also has outbursts. You can see this immense coronal mass ejection taken off here, and both will have of course, affect how comets emit X-rays. And then the final thing, most applicable here, is that there's a lot of interesting spectroscopy that you can do from comets. You have typical, on the right here, I've shown about 10 different comet spectra. And what you can see, these are low resolution spectra by Chandra, and you see emission from carbon, nitrogen, and oxygen. And depending on the freezing temperature of the solar wind, you're going to have spectral changes. So on the top here, you have a spectrum from a relatively cold solar wind, and at the bottom, it's so much hotter. So what you have here is much more oxygen 8 plus over oxygen 7 plus, and here the spectrum is dominated by carbon and nitrogen. Now, the reason why I bring this up, and that's going to be the next slides, is that we're very interested in the chemical composition of comets. So there's a lot of information in this plot. This is the average chemical composition of comets with respect to water. So at the top, there's 100% water, and you see that there's a lot of CO and CO2, although this varies a lot between different comets, and a bunch of smaller molecules here, all at the percent level. So these are our main gases: water, CO, and CO2. And one question that I've always had is, can you use the X-ray spectrum to see how much of those is there in comets? Because CO2 cannot be observed from the ground; it's observed by our own atmosphere. So for that, I used the wonderful Cronus package that was described by Millen in 2017, and that is freely available from Phil Stansel's website. And I generated spectra for, in this case, for water, which is the black lines, for CO2, and for oxygen, green. And so what you can see is that the Cronus package clearly predicts that you get different spectra for carbon-bearing molecules versus those that are from the water group. So for the carbon-bearing ones, you're going to have this group of lines, the forbidden, intercombination, and resonant line, are about equally strong, whereas for the water group, the forbidden line is much stronger. And then also you see here in the K gamma and the K delta, you're going to have the gamma in case of the water group. No, I say that the wrong way around. The carbon group, and the delta in case of the water group. Okay, so you expect a clear signature there. Now,
1 minute you left.
Okay, of course that's theory. So I went and found a actual spectrum of charge exchange coming from carbon dioxide. I looked at the spectrum obtained by XMM from Mars, which, in my naive thinking, had an atmosphere of mostly CO2. Spectrum is shown here to confuse you all. It's in units of wavelength rather than in units of energy. And what I saw is that the strongest line is the K delta. Now, did that make sense? K delta, that's the one here. However, it turns out the spectra that were acquired of XMM have a very large field of view, and what you see is the exosphere of Mars. So you're mostly looking at atomic oxygen, and that again is in line with what you would expect from the Cronus package. That was a very quick presentation, but the slides will be online. There are going to be 2 more presentations from our group, one by Emanuele at 11:45 and at 10:11 by Steve. Thank you.
Great, thank you. We have 45 seconds for questions. Are there some questions coming up? Let me ask, can you use any of the rovers on Mars to get spectra that are useful? You know, Curiosity and Perseverance and all those little devils.
They're really more focused on minerals and zapping rocks and looking at the spectra of those rocks.
Well, they do image stars.
They have actually, yes, and it's very difficult because they're not built to find objects or track objects on the sky. They actually did observe a comet that flew really close by Mars, and NASA was really concerned about their assets. being hit by the dust.
Okay. And then there are dust storms and other things.
Yep.
Okay. There's a question. Why are the speeds from the sun lower in the plane of the solar system? From Arjun Dawn to you. Why are the speeds from the sun lower in the plane of the solar system?
I'm not a heliophysicist, but they come from different sources. So in the equatorial plane, they mostly come from different sources, and that results in different escape velocities as well.